Welcome back to the class of Calculus 3. This time we are moving to section 4.4 tangent planes. First, maybe just to clarify, this is in chapter 4, mostly chapter 4, it is for function of two variables. So I said here, the graph of function of two variables is a surface. Let's assume without going through all the details, we are going to have a smooth surface, okay. Like as showing on the graph in the graph, and at any point on a smooth curve, you can draw many tangent lines in different directions. And actually, we are going to talk about tangent lines again, and we are going to talk about directional derivatives in the next section. Okay, but anyway, let's say just say we observe there are many tangent lines, and indeed, if you do it carefully or if you think very carefully, all the tangent lines will stay in the same plane, and that plane it is tangent plane. Tangent plane, it is a plane formed by tangent lines. That should be it. That should be it. Okay. And then the question is, how do we figure out the equation of the tangent plane? I hope you remember, well, the equation of a plane actually turns out to be linear equation. Linear equation. So we do have the formal arrangement for the linear equation. And also this time to write out the equation of the tangent plane to a function. I'm not going to give any explanation. If you're interested, we can discuss the situation maybe at a different time. And for now, I'm just going to present the result. The equation of the tangent plane to this brownish or orange colored surface. Okay, at a given point, x naught, y naught, z naught simply can be arranged as this fashion: z minus z naught times partial derivative at point x naught y naught times x minus x naught plus partial derivative with respect to y times y minus y naught. That is the equation of the tangent plane. And also, if you are reading the textbook, this is how the equation would look like. They are equivalent, right? You see that. Certainly, z naught is represented by f of x naught, y naught. They are the same, right? They are the same. And the reason I want to show this first form, I hope you remember, earlier we did the equation of a plane in the three-dimensional space. This is somewhat consistent to what we did before, okay, what we did before. And in this section, I only got one example. Hopefully it should be easy. Okay. This time we are having a surface. It's given by this function. Pretty much complicated. I have no clue how the surface would look like. But usually when you have a function given by a formula, it's fair to say the surface is smooth. And so we do have a point on that surface. And we want to find out the equation of the tangent plane. We want to find out the equation of the tangent plane. So I say you can either use this form or the other form. Clearly, there are partial derivatives involved. So first I calculate partial derivative with respect to x. One more time about partial derivatives. 3x squared, 2xy. This part goes to 0, minus 2. And the other two parts goes to 0 again. Partial derivative with respect to x. And x naught, y naught, it is at the point negative 1 and 3. So I plug in this ordered pair for x and y into here. So f sub x at this given point, my calculation is 7. You help me double check with the number, okay. Number 7. And then similarly, partial derivative with respect to y. Derivative of x cubed, that's 0, and the minus x squared, that's 4y, plus 2y, and then plus 3. And similarly, I plug in the same order of the pair for the partial derivative with respect to y, and my calculation is 8. And still help me to check if that's all right. And then finally, I'm having z naught. Z naught, it is the function at x naught, y naught. So f of -1 and 3. Plugging this order pair into the original function, not the partial derivatives. And my calculation says 10. I suppose 10 should be all right. And then finally, the equation of the tangent plane simply can be, well, I copied on the equation of the tangent plane. Somewhat I use the arrangement as on the textbook. But anyway, the other one really the same. Okay, z equals 10 plus this part is a single number partial derivative with respect to x at the given point. X minus -1, certainly that is x plus 1. Then plus partial derivative at y, partial derivative with respect to y at the same given point. I got this 8 times y minus y naught, y minus 3. That is the equation of the tangent plane. I really believe that should be it for this section 4.4. Tangent planes. Thank you for watching.